Okay, so let's get started. So we're gonna start from, I think they we did just the protobufs. So we start with loading and parsing example, which is on the 899. Let me check. Oh, I'm gonna just share my screen probably. Uh,
So I think we read to pay encoding categorical, no? But we didn't discuss up to there, if I remember correctly.
Yeah. So encoding category, yeah. I think we read it, but there was no discussion, and I was looking at the comments which Joseph puts in. So they are going to cover this guy, loading parse examples, and then going next to handling list of list using the sequence example protobuf, and then afterwards pre-processing the input feature. So we try to cover the whole pre-processing the input feature all the way up to um, embedding, and I think maybe if we can get to, where is that? Just a TensorFlow transform, just before the TensorFlow transform. After here.
Okay.
Oh, yeah, okay.
Sound good?
Yeah, sounds good.
We will see. If we cannot do the embedding, we'll just leave it. Maybe on a Sunday. He was saying we're gonna do it. Let's see how much we can cover today. But
Okay.
I was just thinking. I think we didn't do this pre-processing in that class, and we didn't do the loading part in that class. So we start from here. All right. And so let's spend next 40 minutes, and then we'll meet at 10 to.
Okay.
Okay. We'll talk to you then.
Bye.
Hello. Sorry, I was I was on a mute and I was looking at the example. So, let me share my screen. There was a lot of to cover, so I'm not sure whether we will be able to do it, but let's try how much we can. Okay, you can see my screen, yeah?
Yeah.
And you can see both screens.
Yeah.
Okay, so I'll try to go, I'm going to switch between these two screens initially, but at the end of, like, if we able to do the embedding, I didn't see an example of embedding coming in here. For some reason, he doesn't have example for embedding. I couldn't find it. So once I reach there, embedding, when he talks about embedding, I'll focus on the right-hand side. Okay?
Okay.
Right. Okay, so let's start this. I think this is where he's starting. So it's quite interesting loading and parsing example. So basically what he's saying is like how to load, how to create the data into protobuf mode, and then loading into TensorFlow TF record, and then it parse it back. So that's exactly what he is talking about here. So if you see here, last time we discussed, like, he just defined byte list, float list, integer list, and then again there is something like features and example. So these are just the objects defined of these types, and now he start creating this the object person example. Person example is of type example. Within example, you're going to have lots of features, and one of the feature is there. So we will see down below, you can have multiple features, so on and so forth. And so that's defined in here. The default value for the name is Alice. It's a byte list. ID is integer. One value is 123, and email is again a byte list, and it has the multiple values in here. And then he goes through it. TensorFlow TF record writer. So it start writing into TF record. It read through the examples, and what you get in person examples. I'm just gonna run it. So that's where he has written. So it's serialized it. And then if I just go and say person example, some example. So that's what he has created, this kind of like a JSON-like structure for you, where you have features. Within a features, you have a feature, and then you have a key, and then you have values. Again, next feature, you have a key, and then you have a value, and then you have another feature where a name and then a value. So that's how the structure has been created for you. And then what the next thing is, next he's talk about when you parse it, you can parse the example which just created here. However, you need to provide the dictionary of the feature. So feature description is the dictionary which get passed to this parsable example. So the description is nothing but two types in this dictionary which are important. One is a fixed length feature, which we defined up here, or a variable length feature. So fixed length would be this, where you have just one value. If you have a multiple values, you're going to define it as a variable length feature. And this dictionary, there's a name of a feature and a type of a feature, fixed length, sorry, it's a fixed length or variable length, type of a feature, and default value. If there is no value coming in, what you're going to display, so on and so forth. So that's defined in here. Now we serialized the example which we have. So serialize the example. serialized example. Okay, so if we go TF record writer, we wrote in a TF record, and here TF record data sets. So we are reading from the TF record data set in a my context TF records, and we have that goes, we iterate through it. The value goes in a serialized example, and we are parsing that through the function parsing function, passed on the value which we got in here, serialized example, and a feature description is the dictionary information which parsing value expected. And then once it passed the values, you get this this kind of information within the TensorFlow. So variable length feature which we define gone to the sparse tensor, and the other fixed length features are gone into normal tensor, then ID and a name. So that's gone into our now a TensorFlow record set. One thing which I don't understand here is, I think we created a person example. So however, here he is using a serialized example. So I think it's defined up somewhere, serialized. So let me check quickly. Control C. Serialized example. Yeah. Okay, we're back here. Oh, serialized example. Oh, serialized.
It is just returned by iterator.
Yeah, okay, it's returned by iterator. So so the example gone into my context.tf records. So it's a reading from this. So that means when we are writing to a TF records, it's a writing into my context.tf records, and then it's a reading from a TF record. I think, yeah, that's right. And then the value goes finally into past example, or here into a person example. Okay, that's the understanding. So that's that, and then you can access the value of now the past example like this. The value of an email, value 0. I think we had 2, so maybe 1. So it's just showing you how you can access the values of those tensors which you define through parsing. And similarly, you can serialize the image. So we have this sample image, just showing this sample image here. And now he's going to go through defining put this image into a TF record, serialize it. And then the way he does is, I think it's called, again, through a parse simple example, as we said. So let's walk it through the way we have done before. So that was your image in here. We got the data, which is in just, we got encode image of the image, which is this, yeah, loaded image. And then we define this example with image as a object of example. If you remember, we define it up. Within it, you have a features. Within the features, you have one feature is image. So I guess you can have the, with the one feature is image, you can have another feature, which is a description of image and so on and so forth. So that's defined here. And then, so that object got created, and this object get serialized to a string. Let's see what does the serialized example gives you. Okay, so this is like all the pixel got serialized, which is in I'm assuming it's a protobuf serialized, which can be shipped to some other language, so on and so forth. And now to parse it back to a proper image, we need, if you remember, we need a feature description. It's an image of a variable length, which we define the dictionary here. And now we are parsing a single example, parsing the serialized example, which is this, and then feature description here. And now, which is gone into a example with image. So now this hold an image, we need to decode this image to display, which we are going to use in here. So enter here, and then I think if you just, oh, okay, so I can do this afterwards. So that this serialized information got decoded back into this, and then we display this. Does it make sense?
Yep.
Yes, no? Okay. And then you can use, instead of using, I think, decode image, he's saying a decode JPEG, you can use decode images. One is the same thing. Yeah. So it's one is the same thing. So you can use either of them, either decode image or decode JPEG. So the gist of this whole thing, which I got it, is how do you serialize? That means this is the information which get shipped to a TensorFlow TF record, and it's going to process it. And then we need to parse it back to what we can read and see through this example, so on and so forth. So we can go either way. One is from normal image to serialized, and then from serialized to back to normal image. That's what my understanding of this whole exercise from top to bottom. Yeah, any question, anything you want to discuss? Okay, again, this is again same example where you have I think this is the list of lists he's talking about here. So that we had an example here, like a simple image, which is just the series of pixels you can see, and over there up here we define sort of like a record, which is one record. However, I think in the next section, that's a JPG. This is what he's explaining in this case. So let me read it loud. So he said, if you have a normal example, it's fine. But once you have a list of lists, things can get a little bit cumbersome. For example, suppose you want to classify a text document. So each document may represent as a list of sentences, where each sentence is represented as a list of words. And perhaps each document has a list of comments, where each comment is represented as a list of words. And there may be some contextual data too, such as document author, title, and publication date. So we are taking a whole, let's say, a book, and then we are going to train it, and then we have multiple books. So we, if you see in an NLP, I think in a BERT they use the, I'm not sure, in one of the architecture they use the Google Books, all the books which they have in their repository. So if you're training all the books, so extracting a feature from all those big books, so you have a feature in terms of the text in a book, you have an author, title, publications, that's a separate thing. People may have commented on it, or back of the page, people do enter about like this small blurb that what this book is about, why this book is good, so on and so forth. So I guess that's what he's talking about, that you will have a list of lists. which is kind of like here, he's defining in here. So you have a list of list. We can serialize. So he has defined just a constant, and then this constant got serialized into s, and as simple as that. And then you can just parse this tensor back. So here, and then you have these value coming back into the array here. And what he's doing here, and we had a past example over there, 2 emails, we had it. And again, he just serialized that those emails by using sparse emails. That's the example he's giving in here. And I think it's just, so that's the serialized information about those 2 emails. And in here, it's converting them into NumPy. And this is going through the record which we have defined, taking a 10 batch of a 10 and serialize them. Yeah, I'm not sure. Is the example we did previously? What's the difference? Yeah, we have done it. So there is nothing special he has done. He's reading from a data set which is in here, serialized example here, and he's just parse example is just parsing. Oh, okay. Yeah, so up here we have been doing one parse at a time. He mentioned that you can do that a batch. So that's all he's talking about here. So instead of you just go one in a loop, you can create a batch, and then you can parse a batch at a time. So that's what he's trying to do in here. Yeah, so that's the list of what he's defining. And again, we have a sequence example. So this one is quite a good example, which he mentioned in this whole text. So how he's going to handle. So if you look at this example here, so we have a feature list, and we have a feature list, and we have a sequence example. So these are the 3 objects defined of these. And now we have defined this context, where in a context has feature author ID. Again, as we define, it's the integer divided is 1, 2, 3. The title, it's a byte list. The title is called A Desert Place, and the publication date, which is the 25th, 12th of 1623. So that's the context he defined. It just, context is nothing but it's just a features he defined in here. Hang on a second. This features is not defined here. It was defined well above. We're going to use this feature list down below. And then you have a list of list. Yeah, so this is a list of list, which has nothing but content. So when shall we 3 meet again? That's a 1 sentence, and in thunder, comma, lightning, or in the rain. So that's a list of example he mentioned up here. And then you have a comments, and that's again the list of like different comments. When the hurly-burly is done, and when the battle's lost and won, so on and so forth. Okay. And now word to features. So here he is going through the words, and then he's just changing into similar to this feature. So we're gonna feed through all these words, and it's gonna create a words to feature. And then I guess finally we're going to create the feature list. So that's just a function created here. Content features. Yeah, so that's where we are putting these sentences. Sentence is nothing but contents. So these contents are going into this function and creating the feature type, which we defined similar to this. You with me? And similarly for a comments, we define here, which is like just again comments. These comments gone, we iterate through, and then we call this function, and then it's going to go in here. Just give me 1 second. I'm going to switch off the. Just give me 1 second. Okay. Now, next is, am I making sense or it's just all blurry? You're good? Okay, I'll take that yes. So now we are creating a sequence example. So that's a sequence example we are creating. We're passing the context. That's our context we passed. And then we created the feature lists. And the feature list has this and this. That's got created in here. So that's what he did. And then actually, once you have created a sequence example, what he has done is, this is a good visualization of what he has done. So he has defined a context. So the sequence example object require a context, and the context contains the feature, key, author ID, and a value this. Another feature is publication date and a value. These are the 3 values in here, 3 integers. And the next feature is a title, and these are the values. So that's the context defined up to here. And the next thing would have that sequence example is the feature list. Feature list will have a feature lists will have a feature list, and feature list will have a key of a comment and key and values. That was first feature. Second feature is another key and values in here. Oh, sorry. So key is a comment. Sorry, key is one key. Comment is a key, and then you have a value, and then you have a value as a feature. And then because it's a feature list, that's why you have comment and a value. And within a value, you have a feature of this and a feature of this. And that makes, yeah, so that makes key this and a value, and whole of these things is wrapped. I think this is wrapped around the value. Yeah, so the key is one and all of them are values. The next one is another feature list for a content similar to the key and a value he has made it. So that's the display of a sequence example which he has created. Once you have created the list of a list or a sequence example in simple words, you just process them similar way. Like sequence example serialized to string, that's there. And then if you see the values, so these are the serialized value of all the everything which we created. And to do the reverse parsing, similarly, we need to create a context feature description dictionary where we're going to have author, title, publication, what type is this, what this size is fixed or various length, whether it's integer string, what would be the default value. So that's the dictionary for the context, dictionary for the features. Once you have it, you can parse it using a parsicle single example, parsing the serialized simple example, which is this, and parsing those 2 dictionaries which we define in here. And once we have done it, this is defined in the form of a TensorFlow, in the form of, sorry, a tensor. This. And then you can access the values of this parsed context by these are the contexts you have. So you access those values as normal as you do. There you go. It's quite interesting actually if you just go through yourself, and once you read it and then you go through these examples, it started making it quite a good sense. Okay, so that was the handling list of list using a sequence example of proto of. And so we did this, and okay, so here the pre-processing of an input feature. Okay, so the next thing is, as I think earlier we did, you can use the map function, or you can include a pre-processing layer directly in your model. So in this process, I think here he's trying to say that you can do pre-processing beforehand, or you can do on the fly. You can create your own APIs or own function, or you can use, I think he has mentioned in front that he has created this standardization, I think, or normalization, he mentioned somewhere. Yeah, normalization layer. So we don't have to do anything if they exist already, so we can just start using it beforehand in the model itself. So the whole point is that we don't do the pre-processing, we just add the layer, whether it's a custom layer where he's saying like, okay, what are you going to do? The normalization, and a normalization, you just subtract the mean and divide by standard deviation, or perhaps you can use just the normalization layer, which he has defined in there. And that's exactly what he's going to do in our housing example. So let's get this quickly done. So this is all about the housing, California housing data set, fetching a data, creating a data set, and that's the data comes into our housing here. So that's how these data set look like. Median age, so this is the column. So we just get into our median age column, and then defining mean age and standard age. If you remember last week, actually these are the columns he defined way above. He just getting those values in the age mean and age standard deviation. And now in here, all he's doing is just a lambda function, I think. Yeah, numeric columns in the lambda function, and then all he's doing is just subtracting the age mean from an x and dividing it by standard deviation. So all in all he's doing is, this is just nothing but a normalization process. He's talking about here. So that's that. And passing the median income, which is median income to, oh, so this is, sorry. So here we created the normalizing the housing median age, and here we got the median income, and oh, he bucketized it. So next thing he's saying is, I think it's mentioned here. Okay, yeah. So this is where he start diverging from. This example is not present in this book, but it is present in the PDF. So all he's mentioned here is if you have this median house value, so instead median income, instead of using this as a continuous column, sometime you have, if you bucketize them into a different bucket, your model may improve. And we don't need to do anything. Actually, he mentioned in here somewhere that we have gone too far. So there is a bucketization layer he has created in Akira's. Okay, it will come somewhere. Like the normalization layer, he has created the bucketization, and that's exactly what he is talking about here. To bucketize these, to create another feature. Okay. Now the next thing is encoding. So that was all up to the numerical columns. That's what he discussed up to here. And now we start getting into how to deal with the categorical feature. So the categorical feature, he he uses the one hot encoding vector, and one hot encoding vector is nothing but just to give the values in the form of a array. If I show you example, here is example. Okay, so instead of using these guys as a 0, 1, 2, 3, 4, we give the so whatever values we have 1, 2, 3, 4, we put them into an array, a list, and then where the value is present is 1, the rest of the values are 0. So that's how we create a one hot encoder value. Anybody else has a better explanation? Anyone? No? Okay, just give me 1 second. Okay. Okay, so let's go back. So one hot encode, one hot vector is nothing but replacing the categorical columns in the form of numerical values. So all we do is, in this case, we create the vocabulary. So whatever categorical columns you're going to have, you're going to create the vocabulary for it. Plus, you will have 1 or 2 extra columns where you're going to say that's a number of out of the vocabulary buckets. So where we're going to say that these are the if our any categorical value which comes during, let's say, training time, which we haven't defined in a vocabulary, those goes into those buckets. So you can define 1 or 2 or more. So that's and then once we have done that, you do just then you map the values 0 to the first one. So index is 0, 1, 2, 3, 4. So these are the indexes, and afterwards we map the lookup table from the static vocabulary table from the indexes to the value. Let's do an example actually. So okay, so this is our ocean proximately vocabulary. So it has the 1, 2, 3, 4, 5 values in here, and then we are creating the categorical column with the vocabulary list. We pass the this vocabulary here, and ocean proximity. This is the label. Let's see, and so default value is -1, number of out of vocabulary buckets 0, and the vocabulary list is this. Okay. So I'm not sure what this column is. It's called vocabulary list categorical column, where it's going to be used, or perhaps in down below somewhere this will get used to convert into one hot encoding vector. So this is where I think he doesn't match what the examples are here with the examples here. So we probably go on a theory part now. For converting to one hot encoding vectors, you actually don't need to change yourself itself. He has defined it's called I think text file initializer. Everybody use it instead. He has defined one of the API. Let me see. Yeah, okay. So this is the API has been defined. It's called keras.layers.text vectorization. So this will automatically convert your categorical columns into the one hot encoding vectors itself. And then this is the example he has given, just how we converted, once we have converted this vocab into this hang on a second, I'm not sure what it is called. So however, this is like he converted these guys, he used this code, and this is where it got converted into one hot encoding vector, or one hot encode. Okay. I'm not sure whether if I'm making sense here or not, but you can interrupt me, or we can do more discussion. Okay, so if not here, okay, so one of the important point he made was like it start getting messy if you have categories, categorical column has lots of categories. For example, you have zip codes or postcodes. So rule of thumb is, if you have less than 10 values, let's say gender or here ocean proximity, then you can use the one hot encoding. If you have more than 50, you should start getting into embedding, which is the next topic. And between the 10 to 50, that's sort of you do some experiment. Either you use one hot, or you can go ahead and then try to create an embedding for that. So that's the important tip he has given in here. So let's jump into encoding, embedding. So what's the embedding? Embedding is nothing but just a trainable dense vector of the representation representing the category. So if I give you example, I think he has given an example. Yeah, so it's just a numerical value of anything. For example, these are the numerical values for near ocean. However, these numerical values have the representation of a near ocean. And these vectors could be of any dimension. We have a 2-dimension. You can take, I think, glove vector as has the 300. And then there is another one is a glove vector. Which one is the another one which we generally use from the Google? Anybody has an idea? What's the name of that embedding which Google gives us?
Sorry, Dinesh, what do you mean Google gives us?
So we have one embedding is glove, which is by the Stanford.
Yeah.
And another one is, I think,
Word2Vec, you mean?
Word2Vec, yeah. It's called Word2Vec, yeah. Word2Vec, yeah. So the dimension of that is, I think, 300 long vector. And the beauty of this embedding is these are the trainable vectors which you train using a gradient descent. I think he has mentioned here. These values are initialized by any random values, and then you use a gradient descent to train these embeddings. and they represent. So these are called representation learning. So they represent something, and if you map these numerical values, let's say in here in a 2D chart, you could see the numerical value of near ocean is nearby to the nearby, and then the ocean, so which is less than 1 hour from ocean, is sort of like a near to inland, and an island is kind of like getting on its own, but it has equal proximity to this. So all in all, that's the representation, numerical representation of these feature of this feature, which can be fed into the TensorFlow model. And one of the example he gave here is a word embedding, and which I was talking about, the glove and a word to back, which is quite widely used in the NLP. And these are nothing but the representation of the words, numerical values, but the representation of words in the X dimension, so the 300 dimension space. And one of the famous example is this. So this is the numerical representation. Let's say we are saying in a 2D space of a king. This is numerical representation of man and a woman. And then what would be the numerical representation of this X? So if you subtract the manness from a king and add a woman feminine part, the embedding which you're going to get, that is numerical value which you're going to get, is going to be falling here, which is very near to the queen. So in other words, the embeddings are the numerical values which you can subtract, which you can add, and they do represent the words in there. So that's the embedding which we can use for our categorical columns. Okay, so the next thing is how we can implement it. The example of embedding is not very much given on the left side, so I'm just going to leave left side now. It's going to keep on the right hand side. So here the dimension is defined as like 2, and then just feed in random uniform length of vocabulary, which is the total number of words in your vocabulary is going to be. And out of words buckets, we define 2 back there. You can define more than 2 as well if you want. And then embedding dimension itself, like how many dimensions you want, and then you get in the embedding in it. Sorry. And you pass into variable, and then the matrix which you get, this is the matrix you have, which is the numerical representation of these inlands which we define in here, and that's your embedding matrix here. And this embedding matrix we can use a feature and feed into our TensorFlow tensor record. Okay, and it's exactly the same he's defining in here. And then within Akira's, we don't do this conversion itself. You can define a layer called Keras.layers.embedding, and it creates the embedding automatically for you of your categorical column. And I think it's same thing. It is just cleaning it, just okay, yeah, so this is one of the important point he was making. One hot encoding followed by a dense layer with no activation function and no bias is equivalent to an embedding layer. So that's, I'm like, I don't have any idea the technical form. Anybody wants to explain it?
Well, he means that embedding layer is equivalent to multiplying one hot encoding matrix for the categorical features by a matrix. What would dense layer without activation and bias is just a matrix multiplication. So effectively, embedding layer is acts the same as matrix multiplication of one hot encoded features by this embedding matrix. But it is computationally more efficient because we don't need to do a lot of multiplications by zero. We just can do a lookup into the embedding matrix.
Yeah, I mean, I guess the dense layer would have to be huge to implement, roughly equivalent of an embedding, because if you imagine that every word has got like its own word vector, and that dense layer for each one of those would have to generate it. So yeah, I mean, from the description there, it seemed to be almost like, oh, okay, you have a one encoding, hot encoding at the front, and you just have a dense layer. But actually, the dense layer would have to be enormous in size to emulate what the embedding would have done.
And probably the embedding layer, if we put the embedding layer itself, rather than doing one hot multiplied by dense layer, it's going to be more efficient.
Yeah, I mean, also it depends on your vocabulary. I mean, if your vocabulary is like 30,000, but you're representing each word vector as like 300 dimensions, then each input would only be 300 dimensional. Whereas to use one hot, you would have to send in a 30,000 word vector. So yeah, I guess for those people who are not really into NLP, this is probably a bit confusing. But yeah, one hot, particularly with some of these really huge vocabularies, is not really a great way to do these things.
Okay, so I think this is the last section, and then all he's talking about is we already spoke. So these are the new. I think Kira is pre-processing layer. It was in development, I guess. That's what he's talking about here. That you will have this layer we already discussed. This is the layer which I missed last time. So he's saying he's creating this discretization layer where you can create instead of a continuous column, you can have the buckets created for them for a numerical columns as such. And this is one of the layer he was creating there. I haven't used it, so there is, I think, example in here. Oh, this is the example he has here. So this is, but he's bucketizing it in here, not using this guy. So this is under, I think he mentioned that he will be creating it, and I'm not sure whether it's already done or not. And I think, yes, so the whole rest is, I'm not sure. I'm like this is in here. All he's talking about is like whether you want to pre-process the data or you can use these number of layers to create on the fly the normalization, bucketization, or embedding. So you can just use the Kira's library and then use on the fly. And I think I didn't get a chance to go this particular. I went all the way to here. Last couple of pages I didn't read through, but there is not much in here. I'll just finish up here. Yeah. Yeah, I don't have much to cover.
Yeah, so I guess the next session on Sunday is the last one for this chapter, isn't it? So, Okay.
Yeah, so so there isn't much like TF transform, and that's pretty much it. It's 2 sections, but yeah. So let's see if they can go through. It's a quite a lot. Last time in last Sunday lecture, we barely managed to move a section, half a section. Yeah.
Oh wow.
That was interesting though. The protobuf, they were quite complicated. I didn't understand. Lots of people had some idea, but the interesting part was the links which people put in. So that's the good part on a Sunday class. They always have somebody experienced who has worked on it or had some ideas. So protobuf, I didn't know that kind of like what do you call the XML or a JSON file types. I knew about it. I never knew about the protobufs.
Oh right. Yeah, it's just another transfer format, but it's not standardized. It's only really Google. They've defined it. Although I don't know, maybe it is standardized now. But yeah, if you want a highly efficient binary transfer format, protobuf is a good one.
Mm. And interestingly, this chapter, especially starting with the TF record, it's going, I think, quite underneath to transform the data to have a very low level, creating a low level data and then running the model, rather than we usually just pile up the layers and then we just feed in the data and then it works. But everybody is going step ahead.
Yeah, I just wondered how efficient it was, because that example they did with the image, it seemed like it was being recorded as an array of integer values. I'm sure there must be mind you, I suppose with Python, efficiency is not always your best concern. Well, your most important concern, is it? Most people tend to write Python that's actually really, really inefficient, but it gets the job done.
Yeah. You mean this example?
Yeah, so there was one where when they extracted it back out, it came back as a NumPy array. And I was like, I mean, that's got to be pretty inefficient to represent things as NumPy arrays when the whole thing is really a byte stream. I don't know, intuitively, it's the mentality I have is I don't like inefficient things. And so I'm always like, why the hell are we representing that as an array? Unless you're going to do some, although a lot of these images are tiny, they're like MNIST type or only slightly bigger. But I was trying to process, there's a Comma AI GitHub challenge that the guy who runs it, he runs it for people who want to get a job there. And there you got to process video, and that's like, I can't remember how many frames per second that is. And that's like it's not a huge image. I think it's about 700 by 700 pixels. But trying to put that in models, oh wow, you pretty soon learn you can't do that. That size alone is too big. You have to really compress it down.
So what would you use then instead of NumPy arrays? So where do you?
Oh yeah, I don't know. I mean, I would probably still stick to some sort of a binary string of some sort.
Mm-hmm.
And not bother with unless I was having to operate it or use OpenCV or something to read it in, because I think it's got its own internal format. Mm-hmm. But I'm not an expert, I must confess. As I said, it's just intuitively when I looked at it, I was like, oh wow, that's looking like that's going to be pretty inefficient. Mm-hmm. But I'm not sure what would be the best way to do it.
Well, but if you want to put something into model, you basically anyway convert it into eventually into float 32. So
yeah, or I suppose pickling it in some way, in the Python's own binary format. I mean, that's probably going to be pretty efficient. But yeah, well, thanks a lot, Dinesh. So I really appreciate you doing these. And I'll try and get in on time because I think I'm doing the next one, which is CNNs and computer vision.
Okay. Yeah.
Thank you, Dinesh.
Cool. Thank you very much, guys.
Yeah, thanks then. Right. Bye.